In this video we're going to look at the unity gain buffer. Now the circuit's drawn down here below. We have our op amp here and we connect our output directly to the inverting terminal of our input. So this means that from our simple op amp rules we can say that the V plus equals V minus, but the V plus equals V minus equals V in, and also the V minus equals V out, so we can just say V plus equals V minus equals V in equals V out. So we can say then that the output voltage here is just going to equal the input voltage, and there's just going to be a gain of 1. The point about this circuit though is that it has a high input impedance and a low output impedance, and it's also known as a voltage follower because the output voltage follows the input voltage. But the main point about that circuit is the fact it's got a high input impedance and low output impedance. So, well, what's the point in that? What does that? What do we gain by having a high input impedance and low output impedance? Well, the whole point of it is that it minimises the loading effect, which happens due to the voltages being divided over a load and a source. Okay, so we'll explain that just now. So if we had a tiny circuit like this, we just had some voltage source. Well, that voltage source, ideally you want all of that voltage to appear across that load there. Now if that little resistor wasn't there, then all that voltage would appear across the load, but the voltage source there isn't perfect, so it will have some sort of internal resistance. Okay, so if we think of it in terms of just that voltage source at the moment, then that internal resistance, there's going to be a little volt drop across that there, and then there's going to be a volt drop across ZL. Now what we want to do is ensure that there's a minimum volt drop across RS and the maximum volt drop across ZL, because we want all of the signal to appear across the output, the load. So if we analyse that, we can say that Vs is equal to, well, the volt drop across the resistor plus the volt drop across that load. Okay, but that's equal to, the voltage is equal to the current times that Rs, so it's just V equals IR, that's Ohm's law, and the VL is equal to I times ZL. But we can work out the maximum value for the current. So the maximum value of the current is just equal to the voltage Vs divided by the total resistance, which is Rs plus ZL. Okay, so it means then that we can rewrite that equation above as Vs equals, we have our Rs and we can replace our I with our Vs upon Rs plus RL. Okay, and again this term here, we can take our ZL and we can replace our I with Vs upon Rs plus ZL. So we can see then that the voltage across this load here is given by this term here, that's the voltage across the load, which is equal to the Vs upon ZL upon Rs plus ZL. We're really just saying that this load resistor takes a fraction of the total voltage, and this resistor here takes a fraction of the total voltage, and it takes it in this format, ZL upon Rs plus ZL. So the point about this is that if this value for ZL is much bigger than the value for this value Rs, then you can see that this little equation here, the ZL is going to dominate, so we could in effect take the Rs out, so we just have our ZL upon ZL. So you can see that in that case ZL would cancel with ZL and the VL would equal Vs. So we would have a maximum amount of voltage would be transferred onto this load resistor whenever our value of ZL is greater than Rs. So really what we're saying is we want this load resistance to be very large, but we want the source resistance here to be very small in order to get the maximum voltage transfer from this point here over to this point here. Now if it was the other way around about, if ZL was comparable to Rs, then the value for the voltage across this load resistor, well, it's going to be less than the voltage Vs, because a lot of it will be dropped across this other resistor Rs, so we don't really want that. So the basic premise is that we want the input impedance to be as high as possible. So this would be the input impedance of another stage, that's ZL. And we want the output impedance, so that would be the output impedance of a previous stage. We want that to be as low as possible, and if we ensure that those two criteria are met, then we'll get the maximum amount of voltage transferred from one point across to another point on the circuit. So that's the idea of using a voltage follower. So if we had, for example, two cascaded amplifiers, so here we could say we have amplifier 1 connected to amplifier 2. So the input voltage would be Vin across these terminals. The output voltage would be over a load RL, so that's the output voltage. So ideally we would want the input impedance to the first amplifier to be high, and we want the output impedance to be low. And then in the next amplifier again we would want the input impedance to be high and the output impedance to be low. So that would ensure that we're able to transfer as much of the signal through the system as possible without having this voltage division effect. So we can do that then by placing these voltage followers along the circuit. So if we see that the output of this circuit here, the previous circuit, has got a high output impedance and a low input impedance, and again between these circuits here a high to a low, and between these circuits here the output in the next circuit would be a high to a low, then these voltage followers will provide us with this impedance that we require. Okay, so that's the main idea of the voltage follower and what we use it for. Okay, thank you for listening and goodbye.